Hello, welcome to part 2 of the Advanced Features video for the Lilly version of the Powerstaxx Tolerance Analysis program. This is the second of two videos going over some of the advanced features of Powerstaxx. In this video, we will review additional options in the direction impact column of the tolerance analysis sheet. Some of those options are for convenience, and others allow a more complex analysis to be completed. Let's start with the simpler options. The first is reference. Use this selection if you want to have a dimension shown in the stack-up, but do not want to have it calculated in the stack-up. One way you might use this is to include an extra dimension in the stack-up as an alternate option. Before we enter a new dimension, let's note the nominal is 0.008 and the variability is 0.0072. Now enter CC1 into stack-up 1 and define it as reference. See that the results have not changed. To compare options, let's reverse the settings for C1 and CC1. We can see the nominal is now 0.007 and the variability is 0.0060. The next options to look at are on the bottom of the drop-down menu. They are plus 0.5, minus 0.5, plus 2, and minus 2. The main use for these options are when dimensions are entered on the Dimensions tab as a diameter, and it should be used as a radius in the stack-up, or vice versa. Looking at our stack-up 1, let's say we want to know the radial clearance instead of the overall or diametral clearance. To do that, we change the minus to minus 0.5 and the plus to plus 0.5. Powerstaxx then multiplies the nominal values and tolerance by 0.5, and the result is now the radial clearance. Now we're going to look at how Powerstaxx can handle a more complicated tolerance analysis. Let's scroll down to stack-up 2, which is partially filled in, including a picture of the stack-up we will analyze. It is a cover on top of a plate with a pin and hole in the parts to position them relative to each other. There is a gap between the two parts, and that is the stack-up we are going to go over. The first two dimensions entered locate the hole and pin relative to the edges of the part and determine the gap between those parts. This one is the larger value, so we enter it as a plus. The other one is entered as minus. The next two are a little bit different. As you may realize, with this type of analysis, not only does the tolerance of the pin and the hole play a role in the variability of this stack-up, but also the nominal gap between those two features, which allow for play or float. They are entered as either pin or hole. This dimension is the pin, so we select pin. Notice down here the variability value turns red. That's a warning that the stack-up does not have a single complete pin and hole pair. We have to complete the pair by selecting hole for this dimension. The red cell goes away, and now we have the results of that stack-up. When a pin and hole pair are selected, Powerstaxx accounts for that in the calculation, so the results are displayed here. Some important notes on this feature. First, the pin and hole must be defined as diameters, not radii. Second, Powerstaxx assumes the pin is fixed and that it is nominally centered in the hole, and the float of the pin and hole are normally distributed about the center. The final option in the drop-down menu is formula. That is used when the stack-up is a nonlinear analysis. Its use is described in the nonlinear analysis video. That concludes part 2 of the Advanced Features video of Lilly's custom version of the Powerstaxx Tolerance Analysis spreadsheet. Please watch the additional videos for more features. Thank you for your time.